I guess the deal is we just sort of dive in, right? Okay. No lengthy introductions. Hello, everyone. My name's Sten Odenwald. I'm an astronomer at the Goddard Space Flight Center. First of all, a long list of confessions to make. I am not a solar physicist. I am not a geophysicist. I am not a high-power engineer. Basically, I'm an infrared astronomer who works on discussions of the cosmic infrared background and things like that. So what the heck am I doing at a conference on the Big Bang? Oh, wait a minute. No, that's not what we're doing here. Here's the deal. After I worked on the COBE mission, working on the cosmic infrared background, professionally I kind of came to something of an end of the road, even though I had an NSF grant going on and another grant with NASA to continue working on the cosmic infrared background with my colleague. But we could sort of see the end was nigh for this particular line of research, at least at the level that we were doing it. So I looked about because I was sort of big into education at that time too. I mean, I always have been. And it so turned out that an interesting NASA program called IMAGE was just about to launch their satellite, and they were frantically looking around for someone to do their education work for them. Well, I figured, okay, IMAGE, all right, that's an imaging system, probably astrophysics, because that's what NASA does a lot of. Well, lo and behold, I discovered it was something that was going to orbit the Earth, image particles and fields in the magnetosphere. Didn't have anything to do with quasars and dark matter, the last that I could figure out. But I said, okay, this is really cool. I'd like to learn something new, old dogs, new tricks kind of thing. And all of a sudden, within a year, I had to come up to speed on a lot of the stuff that you folks sort of take for granted. The plasma physics. I was a general relativist, so I worked with a whole different set of equations that were my comfort zone. Last time I worked with Maxwell's equations was in graduate school, and I had a pretty arrogant attitude about them. Pretty messy, large-scale fields, charges, currents. It was just too messy. Well, it all came to roost now, professionally, when I now had to be an educator and talk meaningfully about this NASA mission, whose role was to study the magnetosphere and plasma physics and things like that. But the backstory behind that was talking about space weather, which was a new concept to me as an astrophysicist, and also the whole idea that space weather could have any impact on me whatsoever. Well, I found that sort of professionally extremely intriguing, all right? I'd heard the stories about solar flares and shortwave outages and, compass needles going haywire. How many use compasses anymore? I don't use compasses anymore. And so I really got into this whole subject of sort of the human impact story of space weather. And as I was looking around, and this was like in the late 90s, I realized that this wasn't a story that people were talking about a whole lot because they hadn't had a whole lot of experience with these subjects, first of all. And moreover, there weren't really a whole lot of effects that people had, as part of their experience, where the sun could actually reach out in a meaningful way and do something to your daily lives, okay? So, of course, the first thing that you do as a scientist entering a new field that you know nothing about is you write a book about it. So I wrote a book called The 23rd Cycle, back when the 23rd cycle was just starting. So this seemed like a meaningful thing to do at that time. It was all about human impacts, going all the way back to Julius Caesar and all the way forward to, satellite outages, things like that were happening currently during the early part of the 23rd cycle. I realized that I had stepped on a kind of an odd subject because although I got a prize for writing a newspaper article in the Washington Post on the coming storms and things like that, my book sold about 1,500 copies. And I figured, okay, this isn't something I'm going to repeat. But I discovered that writing articles about it and sort of going on the stump for the community was probably a better thing to do anyway, because I'd come into contact with a lot more people. 100,000 people read an article that you write. 1,000 people bought my book. So, the calculus was very simple. And so, of late, I've been doing a lot more, sort of French fry, bite-sized articles talking about different things. I also got a little bit involved, because I'm a scientist, in this whole subject of, how do we model, what the impact is going to be to us. And I looked at the power grid. Well, John Kappenman and David Baudelaire had already been starting that stuff up in the late 90s and early 20th century. So I figured, okay, I'm going to take a subject area that's really kind of interesting and pretty uniform, and that's going to be the geospace communication satellites. Kind of a uniform population of test particles, and we'll try to model what happens to this ensemble when you hit it with different types of space weather events. I'm going to first go through a little bit of this discussion to talk about exactly what those events are like on technology, but we're going to revisit this whole idea about how you model the impacts and what do you get when you try some fairly simple models. Okay, so, incidentally, National Geographic July issue, our illustrious leader has 2 quotes in it. Carol Schreiber, yes, got 2 really lovely quotes in here about what happens when you have a really big storm come by and rattle your system. You're also welcome to grab some of these reprints from Scientific American on an article that I wrote with Jim Green, modeling sort of the impacts of a superstorm. So I've got 29 copies, and I understand there are 32 of you. So I will intercede in case there are any violent altercations about who gets what. Okay, so let's just start going. The outline of my talk is basically this: a little bit about space weather in terms of origins as the physical system. Then we'll launch into a 3-hour or 4-hour discussion about the impacts, followed by a little bit about space weather forecasting, how that process has improved over the years. The rather complicated issue of modeling the societal impacts in a variety of different scenarios. And then the subject of how worst-case scenarios and preparedness is now becoming sort of in vogue. At the beginning of the 23rd cycle, nobody really knew about any of these things, and it was really hard to write popular articles about things that people had no experience and considered to be very benign things. The worst thing that they could think of if you had a space weather impact was to go out and see the aurora. And to most people, that's not a bad thing. So, difficult story. Okay, for basic physics, well, we're in volume 3 now of this Heliophysics summer school, so you have lots of in-house references and resources for talking about the various aspects of the space weather mechanism, from the base of the convective zone in the sun all the way out to geomagnetically induced currents on the surface of the Earth. So basically, cradle to grave. There are articles that are already in your collected volumes that speak to these rather nicely, so I'm not really going to go through them. The main problem is that we orbit a G-type star, which has a subsurface convection zone. A-type stars don't have this. They're basically radiative zones all the way to the surface. And it's very, very hard to find magnetic fields on A-type stars. There are a few that have them, but generally convective zones seem to be a prerequisite for having magnetic fields on the surfaces of stars. And the base of the convective zone, the so-called tachocline, identified through a variety of helioseismology techniques, seems to be the preferred place for generating the subsurface fields that then get convected up to the surface, amplified in the sunspots and active regions, and so forth. So we orbit a magnetically active star, and we understand quite a lot about that phenomenologically. It all has to do with magnetic fields, large scale, small scale, any variety of scales. And, of course, a very important process called magnetic reconnection. If we didn't have this process, then there would really be nothing more than just a static field on the sun, not changing in time, not doing much more than perhaps producing the solar wind, if that. You really do need some way of transforming the stored energy in a magnetic field into thermal energy and bulk kinetic energy. Otherwise, you don't get flares, you don't get mass motions, you don't get local heating, and all of these wonderful things that we associate with solar activity cycles. And of course, now we have wonderful high-res HD TV imagery of solar flares that are really quite gorgeous, and one can actually localize exactly where the flaring events and the reconnection events are taking place on our star, which is just a lovely thing that we didn't have available to us at the beginning of the last solar cycle for the most part. Somehow, the reconnected fields on the small scale turn into larger scale things, which then become unstable and produce the large bulk motions that we see in coronal mass ejections. The origin of these large scale fields that become unstable is still something of a conundrum. Don't quite know exactly at what level in the solar sort of onion these fields are produced. If they're produced by small scale fields on the surface of the sun that diffuse and reconnect into larger topologies, that's one favored way. And there seems to be some support for that, in fact. But be it as it may, once you have a large destabilized field throwing a large amount of material into interplanetary space, you have what we basically call a coronal mass ejection. And it's basically a magnetic plasma, and as many of you know or will soon know, those things have some interesting properties, especially when they run up against pre-existing magnetic fields in certain planets like the Earth. One has possibilities for dynamic pressure producing basically a magnetopause kind of a configuration in a planet, which varies depending on the ram pressure, the b squared over 8 pi plus rho v squared, which is acting on it. And then because we have magnetic fields on the Earth, which might be different than those in the incoming plasma, we have reconnection events on the sun side of the Earth, and that's answered by another set of reconnection events in the geotail, which then produces field-aligned currents and just this entire ensemble of events that leads to the aurora borealis, amongst other things. In transit, we have an interplanetary solar wind, which can have a complicated structure. We have high-speed wind streams, which come from open coronal holes on the surface of the sun, which then become conduits for fast-moving plasma from the surface, and that propagates along these field lines out into interplanetary space. We also have the coronal mass ejections, and just an ensemble of things which make interplanetary space a very complicated medium and a very dynamic one. In this particular model, one can see a coronal mass ejection reaching the Earth, have a scale change here, and we see the consequent effects. And these were sort of state-of-the-art simulations a decade ago or so. We now have dramatically different simulations now because we can follow a lot more particles at a lot smaller time domain, and you've seen the results of some of those, or will soon see those in subsequent talks. Once that material gets to the Earth and we have a storm time event or a substorm event, then we wind up with things like the aurora borealis, the polar ovals, and also there are consequent effects on the surface of the Earth, which can be measured by magnetometer stations around the globe on the surface. And there are also effects that happen below the ground in terms of the Earth currents that move around as a result of magnetic induction. So it's a complicated environment, and it's not surprising that in such a complicated environment you're going to have things that couple to that dynamic environment in different ways, and some ways that you don't necessarily want. In particular, you have technologies that can couple to that technology either for radio propagation regions or other operational reasons. And so, for the last 150 years, whenever we've had solar storms and technologies that have been deployed, we've always had problems with the technologies, starting with telegraph systems, then moving to long-wave and short-wave transmissions, transatlantic cables, and it's been sort of this unending, as soon as we deploy something, we discover that it has a vulnerability to some aspect of space weather. And then there's a lot of effort made to try to mitigate further impacts and increase the reliability of these systems after they've been deployed, which is actually the wrong time and the most expensive time to be addressing this problem. Perhaps the only industry that has really gotten ahead of the game is the satellite industry. Because mainly satellites come from the space program, and amongst the earliest launches of technology into space, the whole issue of the Van Allen belts and space weather was a very obvious thing that satellites had to deal with. In fact, the first satellite to suffer the effects of space weather was Telstar, first commercial satellite. It actually stopped working, and it was discovered that a high-speed, high-energy particle had basically generated excessive charge on some gate on a transistor in the satellite that was preventing it from operating. And so they took the rather risky move of turning the satellite off, waiting a few minutes, and then turning it back on. And that cleared up the problem. But that was the first time that we had a space weather impact on a commercial satellite. And since then, satellites have been developed with space weather firmly in mind. One can argue about the recent effectiveness of those designs, but nevertheless, the modern satellites come from a very long road of improvements on previous models, and the general trend has been to make them more robust for the most part. So space weather, if you look at it in terms of impacts, there are sort of two flavors of it. There's sort of the ongoing bad hair days, if you want to call it that. These are generally produced by cosmic rays. You can't really turn cosmic rays off. The flux of high-energy particles into particularly satellite technology is generally not a good thing. Cosmic rays are especially bad because they're at sufficiently high energies that when they enter your shielding, they can produce secondary showers. So if you use too much shielding for these high-energy particles, you actually make your radiation background inside the satellite higher than if you just let the darn thing pass through, and take your chance on it hitting something or not. So there are now sophisticated programs that model shielding convolved with fluxes of particles at various energies and energy spectra to get the shielding just right for the level of radiation that circuitry can tolerate. And that's sort of an ongoing development over time as the industry gets more familiar with sort of extreme space events, which they call the worst case scenarios. So anyway, cosmic rays, essentially when they enter a satellite, there's a chance that one of these particles will enter a piece of circuitry, produce excessive charges somewhere, that'll upset a gate, changing it from a 0 to a 1 state when it's not supposed to, and you can see a cascading set of problems changing that way. With solar wind coronal holes, you generally get milder geomagnetic storms. You don't get the really great ones that you see at night. You get more diffuse glows and things like that. So they're significant, but they're not the major things that we talk about when we talk about space weather events. For those, we have to go to sort of the second column, which is the solar storms, the transient events. Coronal mass ejections are this plasma released from near the solar surface, propagates through the inner solar system at anywhere from 200 kilometers per second up to 2,000 kilometers per second. And arriving here either within 3 days or within 20 hours or less, depending. Basically, plasma magnetic field, the arrival time is pretty quick. But in most cases, thanks to chronographic instruments, we can actually now see them sort of on their way. And what they look like is what are called these coronal mass ejection halo events. If it's directed right at you, you basically see this expanding glow around the eclipsed sun that sort of expands out and fades very quickly. There's also a soft X-ray diminution at the same time. So you can actually use the soft X-ray flux from the sun, to detect whether or not it's a halo event or whether it's a backside event. As you can imagine, the material can be shot off either opposite your direction and it'll look like a halo, or in your direction and it'll still look like a halo. So just seeing a halo, you've got a 50-50 chance that it's actually directed towards the Earth for each one that you see. Now halos, coronal mass ejections are actually kind of a dramatic event when they're near the surface of the sun in the inner corona. You tend to form a lot of shocks. The shocks through Fermi acceleration or other mechanisms tend to accelerate particles to near relativistic speeds. And so those particles leap out into space and arrive at the Earth within a half hour or so, and they pass through any satellite along the way, which is a bad thing. The solar proton events are at somewhat lower energy than cosmic rays. Cosmic rays can go up to several hundred MeV or even higher than that for their electrons. Coronal mass ejection solar proton events kind of roll off at about 20 to 30 MeV for the most part. But even so, even at those energies, the shielding issues are still rather complicated. So anyway, if there are no SPEs associated with the CME, then basically you still wind up with a magnetic storm event, fairly large one in many cases. Magnetic storms produce DBDT. You have the production of an electrojet current in the upper ionosphere. That induces currents flowing in the earth ground. And those earth ground currents basically find their way into various technologies like electric power grids, which is a bad thing. So coronal mass ejections, whether they produce SPEs or not, are still bad and the things that we worry about the most in terms of electric power grids. Those that produce solar proton events, in addition, you have the additional problem with satellite anomalies that can be fatal in some cases. If you change a 0 to a 1 in a command bit and you don't catch it fast enough, all of a sudden the satellite veers off and is pointing somewhere else, or goes into a mode that's not recoverable, or some such complicated thing. If the bit flip appears in a data bit, it's just a momentary hot pixel that you don't worry about too much, and you just sort of move on from that. So the anomaly is typically a bit flip type anomaly in a digital circuit. But the criticality of that depends really on where that bit is located in the entire flow of information that's going up and down the satellite. Okay, now for solar flares, we have a whole other set of things. They produce some energetic particles from the site of the flaring event, from the reconnection event. That's because typically 10% of the total magnetic field energy that's annihilated in that region goes out as electromagnetic energy. The rest goes out into local heating and bulk flows. So actually, solar flares are fairly inefficient in producing electromagnetic radiation, but they tend to produce it at the very highest energies, including gamma rays. You could actually have effective temperatures that are as much as 20 to 30 million degrees within a solar flare on the surface. So if anybody ever asks you, at where is the sun the hottest, it's not only in the core, but also in solar flares at the surface, which kind of throws people off very often. So energetic particles, they're basically like the solar proton events, and they lead to sort of the same types of hubris in satellite electronics. The X-rays, an interesting thing with X-rays, people tend to focus on them, and you look at the sort of way people talk about it in the media, and it's like, oh, we got an X-ray flare, and that's really horrible. Basically, X-ray flares do two things. They heat up the upper atmosphere, which is actually bad for low Earth orbit satellites because it increases the, it increases the orbital friction, causes orbit decay, things like that. They also produce sort of this ionization in the ionosphere, and very often in the D layer, and that's what leads to shortwave problems. all of a sudden the D layer, generally short wave reflects off of the higher F layer and then back down to the Earth. The D layer lies below that. And so when you get excess ionization in the D layer, you wind up with increased absorption at shortwave frequencies. And so you wind up with what are called shortwave fade-outs. So that's what X-rays do. They don't do anything necessarily to satellites, but they do a lot to the upper atmosphere and to the ionosphere. And so that's really their major source of problems. And so that sort of gives you a general idea of the kinds of discrete events and where they place themselves in the sort of general constellation of space weather. Now let's take a look at some storms from the past and how things have stacked up. These are some of the biggest geomagnetic storms, basically ranked in terms of their DST, their storm time demagnetization, which is basically what you would measure from equatorial magnetometer stations. Basically, the DST changes as the strength of the ring current changes. Basically, what you're looking at is from the top to the bottom, a decreasing strength in the ring current as you go down the list. And you'll notice that basically all of the cycles in the last few are pretty well represented. We have, of course, some standouts. Let's see, October 29, 2003 is the Halloween storm, about minus 387 nanoteslas. 1989, March 13, the one that took out the Quebec power industry for about 12 hours. That's sort of at the top of the list at this point. We can also look at another characteristic of, instead of using a magnetization parameter as an indicator of magnetic storm strength, we can look at an auroral index, basically how strong the aurora were during this period, and those basically are related to each other. And one finds that the current era, going back to the beginning of the space age, has been sort of, there have been large events, but they have been sort of far between, okay? When we get earlier than 1960, however, we see things bunching up a lot more, and we have actual storm periods. One period from 1958 to 1962, another one around 1947, another one around 1941. But in the modern era, they seem to be, not so much equally spaced, but they come and then there's a long period of time when people can forget about them, and then there's another event, and then there's a long period where people sort of forget about them. But in these earlier episodes, you had so many happening very quickly that they really embedded themselves in people's psyche. That, we've got another solar flare going off, and all kinds of shortwave outages happening and things like that. Most severe X-class flares. This is an interesting list, ranked in terms of 1 to 10. The November 4th, 2003 event estimated at X45 on their scale is sort of the top. And we don't know of any earlier than roughly about 1970 because people weren't measuring X-rays from space at that time. So we don't know what earlier periods were like. Cycle 21, there were about 5 of these events. 22, there were about 9, and in 23, there were 5. It's all small number statistics. One can argue that these numbers are all comparable to each other, maybe with 22 having a little bit more oomph, than the others, but, it's a difficult call to make. The total number of X-class flares in cycle 23 was 122. So, the number that, the total number of flares, C, M, and X, was about close to 15,000. So clearly these X-class flares are only a 1% effect. And of that 1% effect, you'll only get maybe 10% of those being in this list or anywhere close to this list. So it's a rare event. You'll get maybe 1 or 2 really good ones every solar cycle. Recent cycle 24, we've had a couple of X-class events, 2012, 2011, but they still haven't gotten up to the level of entry into this list yet. Okay, solar proton events. This is an interesting collection of things. These are the fluences of energetic particles coming from coronal mass ejection shock events. The most intense one at 43,000 particle flux units was 1989, October. Actually, no, I'm sorry. No, 1991. I'm looking at this in a kind of a tilted way. And it goes all the way down to about 5,000-ish or so. Typically during a sunspot cycle, you'll have 3 or 4 years during sunspot minimum where you don't have any solar proton events at all. And then you start seeing more in about the 10 to 100 range. And then you get a few that are up in these, at these levels. These are the ones that are the most problematical for satellite technology. We are extremely well shielded down here, so they don't present any kind of human issue. They could present an issue for astronauts working in spacesuits, additional radiation dosage, and things like that. So that's an issue. Worst case storm events, we've had about 5 or 6 really bad storms, and they've been bad in different ways. Some are bad because of their travel time being very short. Others are bad because of their total particle fluences. The 1859 storm is sort of remarkable because it's sort of in the upper levels of all of these potential ranking strategies for a worst storm. And that's why 1859, the September 2 event, is considered significant. And in fact, it's one that we're now developing enough background information about that we can actually characterize it accurately enough for modern satellite developers to actually use this as a worst case event. Because they were previously using events in 1972 or 1991 as sort of the worst kind of radiation event that their satellites could experience. The problem is that this 1859 event is like a once every 150-year event. These other 1991 and 1972 events, you can have maybe 3 or 4 of those a century. So, it's up to you what one wants to call a worst case event. And when you get to 150 years, you can argue that you're getting towards the long end of a meaningful, calibration scale. However, if the event is big enough, even a rare big event is going to be something that you want to take notice about. And we'll get back to that a little bit later. Technology and impacts, it's a laundry list of just about every kind of thing you can think of. Severe psychic anxiety, perceptions of cities on fire. It runs the gamut when you read these old newspaper accounts. Satellite failures and upsets, air travel issues, GPS positioning errors. We've seen it all. And this is what's so complicated about space weather events, is that it's a frustrating thing because you can have 2 satellites that are literally in the same region of space, and one is going to get hit badly, and the other one, not a scratch. And this is what gives the industry sort of the license to say that these events are really not space weather events at all. They're all about, the manufacture of the satellite or some internal issue that didn't have anything to do with space weather. The space weather at the scale of the sun and the Earth should be kind of a global thing that should affect all of the satellites, at least at some level. And most space weather events, even the big ones that we know about, if you go back into the satellite logs, you find most satellites seem not even to be affected by them at all, which is probably a good thing and a statement that the satellite industry has really developed a product that's extremely robust. Or it could just simply be selective reporting, which is also a possibility. This gets us to sort of an interesting subject. If you go back and look at, we know when all the big geomagnetic storms happen because we've got various indices going back quite a long ways. If you go and look at the New York Times for all of these dates when there were large geomagnetic storms or sunspots or telegraph outages, you discover that the number of articles written about these things changes sort of sluggishly with the auroral activity index. So the big auroras get lots of newspaper articles. Small auroras tend not to. There's nothing new here. This is not rocket science. And you can even argue that kind of a trend line is not sufficient and it basically is consistent with there's no trend whatsoever. What is interesting, however, is when you look at the average page number for where these storms are being reported. Up until roughly 1950, they tended to be reported within the first 5 pages of the newspaper. After that, they tend to get buried further back in the newspaper. They're not on the front page of the New York Times anymore. And so one can argue, probably plausibly, that, and here's a column lines, the number of actual lines of discussion that are devoted to these events. You see that also roughly around 1950, there was a drop, a rather dramatic drop, I would think, in terms of how much space people were actually giving to space weather events, whatever they were. So not only were these stories in modern times sort of relegated to back pages of newspapers, but the actual size of the article shrunk by almost a factor of 5. So the general public, after 1950, even though space weather hasn't changed, we still have as many events per cycle as we ever used to, the general public is becoming less and less aware that space weather is even an issue any longer. It just doesn't get covered very well. Yeah, go back to 1930. This is front page of the New York Times. You know, this is the standard. Every time there was anything going on with the sun, front page New York Times. You know? So let's go through sort of one by one all these technologies that we know about and sort of get an idea for how they're vulnerable. Radio communication, first half of the 20th century, this was largely shortwave communication. And here you have the situation that whenever you have an X-ray flare, basically it causes the D layer to become more absorptive, and that cuts back on basically shortwave communication. So you wind up with a fade-out effect. That can last for quite a few hours during the daytime, and basically was a real source of concern for the military in the 1940s for very obvious reasons. Now, today, does anybody care about shortwave anymore? How many of you are ham operators? I'm not saying that negatively. I'm saying, you know, before, in the 50s, there were a lot of people that were plugged into shortwave in the 40s because that's how we were getting our news, primarily. Before the age of the television, getting it through radio and shortwave. In recent years, I mean, the number of shortwave stations has really plummeted from a high back in the 1950s, and I just started this in 1973. Basically, they're predicting that shortwave stations, except for ham operators, are going to be largely extinct in another 15 years. But the thing is that even though space weather can affect shortwave, and shortwave is no longer the favored way for people to get information, it does play a role, a rather unique role in disasters. In fact, ham operators tend to be the only people operating during major disasters to get information around. And so there is still a very valuable role to be played by shortwave operators. But it's not, you know, commercial shortwave broadcasting, it's not news, it's not entertainment, it's basically emergency broadcasting, which is still pretty soundly the way that shortwave is used these days, for the most part. That and religious broadcasting, which is one of the largest operators on the shortwave band these days. They have the most radio stations. But even their religious stations are moving to the internet for broadcasting, as is just about everybody else, because it's so cheap. A shortwave station is actually quite expensive to operate, so that's a cost issue. Another thing that comes in is submarine cables. In the 1800s, when telegraphy was the way to get information around, the first transatlantic submarine cables were installed between the United States and France and England. The first few of these were failures, mainly because they burned out. They burned out because they wound up with extremely high voltages that burned, or currents that burned through the insulation, and that was a real problem. And they basically tied that to space weather events, particularly what are called ground currents. It turns out that submarine cables are our closest contact with the old telegraph systems. Even though telegraph systems are long gone, telegraph systems and submarine cables work on the same principle. You've got some kind of a signal passed down a line which requires either repeater stations along the line or some other way of boosting the signal. Now those repeaters, whether it's a telegraph line or a fiber optic line, have to be powered. And the way they're powered for fiber optic cables, and here's a kind of a map of a few of the fiber optic cable setups around the world. It's a pretty dense pack across the Atlantic. I imagine whales can easily trip on these things if they're not careful. The way that it works is that you have basically high voltage sources on either end of a fiber optic cable, one at positive voltage, one at negative. But one side of the high voltage supply is grounded to the earth, and the other side is what drives the repeaters. So, as I mentioned before, you have these things called geomagnetically induced currents that come from basically the induced current from the auroral electrojet induced into the ground system. Those GICs, they flow through the ground, and they very easily flow through these high voltage junctions and cause upsets along the repeater line. For telegraph systems, what happened would be that the telegraph sets, it would be a single line telegraph cable that would be strung up between the trees, and one side of the battery would be attached to the line, and the other side would be attached to the earth ground. And so when you had GICs flowing in this situation, you could easily have several hundred volts of GIC voltage, or the equivalent amperage for the resistance of the cable, flowing through this network that overpowered the batteries that were being used. And this was a regular happenstance. In fact, in many cases, it led to devastating fires and people screaming down the streets and things like that. So it's kind of interesting that we've gotten rid of telegraph systems because they're inefficient. We've adopted fiber optics, but we've still left in place the original vulnerability. Computer systems, as I mentioned earlier, we've got circuitry. The circuitry has gates and junctions and traces, conducting traces between the various substrate elements. When you have a high-energy ion passing through this material, it leaves behind a trail of charges. The charges collect where they're not supposed to collect, saying that poetically, and you wind up with a gate in the wrong state. That gate can be pushed into the wrong state permanently, in which case it's called a single event latch-up, which sometimes cannot even be cured. Basically, you have to reroute your software so it doesn't use that particular combination of gates any longer. Or if it's a single event upset, you can sometimes repair that condition just by basically resetting the processor or basically doing something equivalent to that. And both of those are effective. So those strategies are well in place. These types of events are fairly well known in the communities that build computer systems, either for satellite use or even ground use. In fact, Microsoft has a patent for a space weather mitigation strategy for its new generations of microprocessors, because the rate at which they're getting these latch-ups and single event upsets on Microsoft processors is at an intolerable level. So they've had to design a mitigation strategy around that. And so even at ground level, they're still seeing problems that are space weather related, which I think is extremely remarkable. Error detection and correction algorithms abound for computer systems that operate under high radiation backgrounds. It can be as simple as working with parity bits. I think most of us understand how parity bits work. Yes? Okay. Yeah? Okay. You've got a digital word, and one additional bit is tacked onto the end of it, so that when you count up the ones in the digital word, if the number of ones is even, the parity bit has a 1 value. If the number of ones is odd, it has a 0 value. So you can determine whether or not a binary word has been corrupted just by consulting the parity bit and checking that it has the right number of ones in the actual word. If it doesn't, then you wait for the retransmission of the word, and that's how you repair it. Watchdog timers, you have a system that has a timer, and when the timer runs out, the processor automatically resets itself. And so if you have any operation running on that processor, it periodically resets the timer, and when it no longer does that, because it's been corrupted by a space weather event, then the timer automatically trips the reset button and everything is fine. Redundancy, ask me twice or ask me 3 times. Polling is very important in avionic electronics and in other situations where you can afford to have several redundant processors all doing the same computation and comparing their answers to make sure that, that the corrupted one is not influencing the final answer. Radiation hardening is sort of the obvious thing that you would think about doing. One way to do that is just to use a lot of lead, cut down the background that the processor or the circuit is seeing. But as I said, for the very high energy cosmic rays, that leads to sort of a double-edged problem that you're actually generating more secondary particles in the shielding, and that increases your risk for failure rather than just leaving the particle to pass through and take your chances. Here's an example of a junction that got hit by a heavy ion impact. Basically, the size of these junctions is now below 1 micron or less in the nanometer range. So we're getting to junctions in these very dense circuitry boards that are only the size of a few thousand atoms. So it's very easy to whack one of these things pretty badly and destroy it, physically damaging it. Mitigation strategies, there are many that have been adopted, and they're all expensive. On the left hand, you see what's called a 6-transistor latch, part of a logic circuit, and the radiation-hardened version of that uses 12 transistors. Well, 12 is more than 6, which makes it more expensive, which means it takes up more real estate, which means there's less real estate available for your memory, and you see where that goes. So radiation hardening, by changing the circuitry to make it more hardened, is an expensive proposition that cuts into profit margins, reduces the capability of whatever the system is that you want to perform. And so, there are trade-offs. Satellites are sort of the quintessential miner's canary for space weather events and effects, because we think that they're places where it's the cleanest kind of physics. You have a high energy particle coming into a satellite through its shielding, and some will do that, and affect some kind of a circuit which causes a logic change, which causes an anomaly in the satellite's operation. And so some operator on the ground then has to countermand what the satellite is trying to do because it got a 0 set to a 1. And the economic real estate represented by these satellites is rather staggering. The total satellite fleet in 2004 was 900, it's close to 1,000 now in terms of operating satellites. Hardware and launch cost, we're talking $250 million in sort of just the hardware itself. And then we have transponder capacity and annual revenue and a variety of other things here. Just to give you a sense that, we have a lot of real estate up there. And it's an amazing thing when you go back and look at some of these big storms that we've had, that not more of this real estate has been damaged. But then who would be reporting the damage? You either have the satellite operators doing it, and there are reasons why they wouldn't want to do that, or you have the system failing in such a spectacular way that your pagers don't work, and then you can no longer conceal that there was a problem with that satellite. Or all of a sudden your ATM doesn't get, transaction doesn't get verified at your gas pump. All these things have happened. And so we don't have a whole lot of ways to determine whether or not a space weather event has actually happened in this real estate or not. And this is just the commercial real estate. For the military real estate, it's totally unknown what goes on there. Satellite impacts, from space weather events are manifold, and it's just about any possible thing you can imagine seems to set these things off, or at least in principle. You can have surface charging events, electrostatic discharges that can damage solar panels. Can lead to high-frequency transients that run through the conductors in the satellite, which cause, gate problems and things running out of spec for a while and all that. Solar cell damage, you can have atmospheric drag because the X-ray heating of the upper atmosphere has puffed it out, which increases drag, and a variety of things. And also there's just the telemetry radio propagation issue, that's also extremely important, especially for GPS systems. The ionosphere tends to be a really messy environment. And the way that it responds to space weather events is very complicated, as I'm sure you've heard. And the problem is that the only way we can communicate with satellites is by propagating signals through this layer. And this layer is highly sensitive to additional ionization from X-rays and other types of events, and ionospheric currents that come and go. So it's a very complicated medium, and that's why there's so much time being spent in understanding the properties of the ionosphere and scintillation and all of these. Satellite outages, there have been a few during the 23rd cycle anyway. That's the list here, totaling just under about $3 billion. You know, that's a chunk of change. For most of these satellites, ASCO was a research satellite, and Equator-S also, but for the others, a good deal of this money was paid back through insurance premiums that satellite operators have with insurance companies. They pay in every year a certain amount of money to get insurance, and if there's a satellite failure, then basically they get some or all of the cost of the satellite repaid to them. So it's a kind of a neat situation. Insurance companies, meanwhile, are space weather experts because, you know, in order to get a satellite insured and to get an assessment on what premium they're going to charge on a particular satellite bus, they require that the satellite owner tell them everything that they know about susceptibilities of that bus type to space weather events as part of the negotiation process. It's all confidential and secret, so we don't really know what are the good buses and what are the bad buses. That doesn't filter down to the public or to scientists, but you can be sure it's part of the discussion that insurance companies have in this high-stakes game. The 23rd cycle wasn't actually too bad. The insurance companies still made huge profits insuring satellites. They only paid out maybe $3 billion, but they gained probably 10 times that. So that's fine, because the 90s and the early 2000s were kind of a very aggressive period of putting new satellites into space and insuring them. Here are physical effects of the space environment. You know, it's kind of a quick list, but you know, these are things that happen. We have low energy electrons, surface charging events. We have high energy electrons producing deep charging within the satellite itself, which is bad because the deep charging events get discharged right near where some of these discrete components are located. And generally, you don't want to do that. You don't want to send off a lightning bolt near a junction or a processor in a computer. You know how sensitive your own computer is to stray electrostatic charges, and so forth and so on. It's kind of an interesting list that I kind of already talked about. Here's some sort of dramatic images that I was able to find. At ground level, you actually get cosmic ray tracks that corrupt images taken by astronomers at telescopes at moderately high mountaintop locations. So cosmic rays, you know, get down very close to the ground. In fact, they reach the ground. They constitute about 5% of your average human background radiation dose. If you're an exposed sensor in space, like this CCD imager on the SOHO satellite, moments after a large coronal mass ejection with a solar proton event, you will get the snow event. That's because the CCD literally is open to space, so it's not shielded. So anything that hits it is going to cause pixels to get hot and things like that. The rest of the electronics with the satellite, of course, are well shielded, and that's why the system actually operates. We can also find other places where space weather, or in this case, this happens to be the Van Allen radiation belts, which aren't really space weather, but they can be modulated by the space weather event environment. Here we have memory upsets in a satellite that flies over the South Atlantic anomaly. And we all know about the SAA. That's where the Inter-Van Allen radiation belt sort of is closest because, you know, we're not talking about the Earth rotation axis and the magnetic axis being coincident. They're actually tilted. So that allows the Van Allen belts a little bit more access to the Earth over this region. And so you get these upset events, and you can actually map out the extent of the South Atlantic anomaly pretty accurately this way. Also, that means that the International Space Station, when it flies over, or whenever any LEO satellite flies over the same zone, it gets hit by the same kinds of problems with memory upsets and latch-ups and things like that. So it is a natural hazard in space that sort of is there. It's like, you know, the Devil's Triangle, if you will. Actually, it's actually not that far away from the Devil's Triangle. That's another talk. The thing that's really horribly complicated about space weather and trying to figure out what it does to satellites is the issue of fluence and occurrence rates, and how you can conceivably construct any kind of a deterministic model to predict if and when a specific satellite is going to suffer a problem from a particular space weather event. You know, if you take a typical communication satellite and you look at the volume of that satellite, during any given year, there might be 10 to the 12 particles flowing through that volume, okay? That generates on the order of about 10 to the 6 of these single event upsets. Almost all of those are harmless for the most part. And then you get, from those, you get maybe anywhere from 1 to 10 actual satellite anomalies that result from this interaction. The mean time to failure, that is to say, it gives you a sense for how long you have to wait for that number of anomalies to actually give you an anomaly that's destructive to the satellite. Typically is 250 years for a typical geocommunication satellite. People that build communication satellites look at that number, 250 years, and say, we're only going to need this satellite for 10 years. Hey, we've made it. We have a robust system. It's going to outlast our conceivable economic lifetime for that system and what it's providing the consumer. And that's, who knows, that probably is a good way to look at the problem. But this gives you sort of an idea. And now the question is, you know, do they really need to make the satellite perfectly invulnerable to space weather events? Well, for them, that comes down to the cost. You know, if you get 364 days of 100% reliable operation in the face of a space weather event, how much is it going to cost you to get that one extra day to give you 100% over the full lifetime of the satellite? They're arguing that it's going to cost us equal to the price of the satellite itself. And at that point, it becomes very non-cost effective for them to even add any more shielding or do anything more to that particular satellite design because they've made it. They've got their 250-year lifetime thing, and they don't need an extra day of reliability in order to extract as much money out of their consumers as they think matches their profit curve, you know, if you want to look at it that way. So that's why communication satellites have sort of stagnated in development, because their worst case scenarios and their past history leads them to this conclusion that they already have a very robust resource. And the fact that during the last solar cycle, you know, we lost maybe 5 or 6 communication satellites, 2 or 3 of those were from understood technological issues. They were deploying a new generation of satellites, and there were a couple of glitches. You know, the argument can be made that the satellite industry has gone basically as far as it can in providing us with a reliable commercial resource that can stand up to just about any kind of a solar event that we want to throw at it. Anomalies that have been reported at GEO. I just thought I'd put this list in here. We got 1 satellite failure, okay? And the rest of those look bad, but generally satellite control processors, there are 2 of them in a satellite, so losing 1 is generally par for the course. And other things are not considered basically issues for the satellite industry. So they look at these severe anomalies that have been reported and say, you know, we've got a good product, we've got no problems. The other way that space weather affects satellites is just from the aging of the solar panels. You have the cosmic ray or solar energetic particles colliding with the solar panels. That produces a general degradation of about 2% per year in power from the solar panel. If you have solar proton events, that can produce a much more dramatic change very quickly. This is the SOHO satellite, and you see the upper red line is this 2% slope, which matches sort of the typical canonical rate of solar panel degradation that everybody works with. Then you have this period where we had several solar proton events, which basically put these solar panels on a different track. which they have now recovered from because there are no longer any solar proton events, and so we now have that 2% slope again. What they do, and I think many of you understood this or understand this, is what they do is they determine what the maximum power is they need to operate their system. Then they determine what the area of the solar panels are that they need to produce that minimum operating power for 100% operation. And then they work out the lifetime of the satellite, 10 years. They multiply it by that 1 to 2%, and so they figure we need to make their solar panels about 10 to 20% bigger, so that by the end of the life of the satellite, this 2% decrease has gotten us still to 100% power that we need at the end of life of the satellite. So we can still run all the transponders that we're getting commercial stuff from and not be sort of impacted by this constant degradation that's going on in the space environment. So that's their strategy, and it's worked. A lot of people use the same strategy for long-term satellite real estate. Cellular mobile phones. This is kind of an interesting story. First of all, it's estimated that by 2010, which was a few years ago, 67% of the human population had cell phones. I mean, that's how far this new technology has penetrated into our psyche as a species. It looks like the curve is starting to roll over. It might be a logistics curve, so it has an asymptote up there, maybe at 80, 85%. And you'll still have, they still show, people living in remote villages in Africa that have cell phones, and bushmen in Australia that are using cell phones. So they must have cell towers, within some reasonable distance of these tribes and villages. And now, I don't know how they afford them, but I guess whatever the equivalent number of sheep and goats they have to use to buy these things, I don't know. There is a problem with cell phones that was discovered by Lanzarote et al. In 2005, and that is the sun is a very active star. It produces type 2 radio bursts. The power spectrum of those radio bursts includes the operating range of most cell towers. So if you have the sun behind a cell tower and your cell phone, you're using it to dial someplace, it's going to see the flux from the solar event in addition to trying to get the signal back from the cell tower to make connection with the cell tower. And when that happens and the noise level becomes too high, you wind up with a dropped call, which I've never experienced drop calls except with AT&T, but that's for different reasons. I don't think that's space weather, that's just the reliability. But anyway, so basically what happens is that the space weather events affect the drop call rates for people using their cell phones around sunrise and around sunset if you're using a cell tower that's in the right line of sight. So a lot of things have to come together the right way in order for you to actually experience this. But it's still there. It's an effect that impacts our new technology. It's not a big impact, but if in your geographic situation you know where your cell tower is, and if it's due east or due west of your house, then you're probably going to have a lot of dropped calls, and that could be a problem if you have an emergency situation going on. So conceivably you can come up with situations where this could be a really big problem. GPS systems, we all know about these. There are getting to be upwards of almost 1 billion GPS enabled devices on the planet at this point. They're everywhere. The GPS system, I don't want to go into too much detail about GPS. It's fascinating, but the general thing is that you need 4 satellites above the horizon. You have to have your ability to connect with these satellites high enough, that is a signal-to-noise issue, so that you get them, otherwise you don't get a reliable position measurement. And also there's the issue of the propagation of the L1 and L2 signals through the ionosphere, which is highly unstable during space weather events. Basically timing signals and things like that can affect the final solution of your position at a fairly calculable rate. So when you have a very severe space weather event, you can have uncertainties of upwards of 100 meters in your actual position. Now, we're increasingly going to aircraft systems which use GPS within 100 feet or so of takeoff and 100 feet of landing, and GPS everywhere in between. And so what this would mean is that during some space weather events, they would not be able to rely on GPS during the final landing or takeoff periods. And so that has issues for airport congestion now and those sorts of impacts. This is becoming a very well-studied problem. Electric power grids, lots of good discussions about that, including one that's coming up by David. We see the effects of geomagnetically induced currents in a lot of different electrical and pipeline systems, so it's not a theory any longer, it's sort of real world. For transformers, transformers can be seriously damaged by having GICs enter the circuitry, the primary windings. Temperatures over 200 centigrade or more have been reported in some of these transformers that are GIC active. And that leads to problems with insulation and punch through and a variety of effects that ultimately damage the transformer. Now, modeling this is actually fascinating. John Kappenman has worked on the 1989 storm and the 1921 storm. The 1989 blackout storm can be modeled very accurately these days in terms of the electrojet and the ground currents. And when you put in an actual model of what the power grid looks like in terms of the transformers and couplers and capacitors and whatever else, you can actually make predictions about how much GIC you should see at each one of the nodes within a grid. And that's sort of the new generation now of modeling the electric power grid in the face of GICs produced by geomagnetic events. Interesting about the 1989 storm, it cost something like $2 to $3 billion in GDP for Quebec. It took 12 hours to resolve. People were in the dark in the kind of cold winter months. I've been up there in March, and it's very unpleasant if you don't have heating for 12 hours. But what is also interesting is that if you look at the subsequent 18-month to 2-year period, there are a number of transformers in the United States that actually had to be replaced over and above the normal wear and tear to these components. And John Kappenman identifies these transformers as sort of collateral damage from the March 1989 event in Canada. The March event in Canada didn't affect the United States. Came close, but it didn't really do anything, so nobody really paid attention to it. But the data from 2 years out shows that there was an actual impact, a cost from this storm down in the United States. Mitigation is a complicated subject and it tends to be expensive. There are a variety of strategies for how to keep GICs out of these very expensive transformers. Small costs include about $500 million, and that has to be taken out of the profit of the electric power grid industry, and they're not happy about that. But there are other strategies too that have been modeled with these grid models. The net effect is that for a 1989 storm, if that basically had not been mitigated against, we would have a lot worse situation down here in the United States. And for subsequent storms in the future that are equivalent to the 1921 storm, the losses would be even greater without some kind of a mitigation strategy in place. Another issue is just basic radiation. If you're in space or in Denver, which we are, you're receiving more radiation from the background than you would if you were at sea level. And the typical annual dose rate averaged over a variety of geographies is about 0.41 microsieverts per hour, very roughly. Cosmic rays in the Rockies, we're at a higher altitude, so their cosmic ray background rate is higher. In lowlands, it's lower. And so that's, if we go back up to this model, you'll see that generally cosmic ray backgrounds constitute about 8% of our total load, radon being the highest, and the fact that we have 150 grams of radioactive potassium in our bodies is also not a very good thing. So stop eating bananas is, I think, the one rule here. That helps. If you're air travel, air travel is, we're closer to the magnetosphere if you're in the air travel than if you are on the ground. You have less atmosphere above you, certainly, by almost an order of magnitude. So there's less shielding. People have studied the radiation backgrounds, number of passengers flying polar routes. Polar routes are especially problematical because they're pretty good entryways for energetic particles into the lower altitudes of the Earth. If you're in a plane flying at typical cruising altitude, you can expect to get roughly about 7 microsieverts per hour. Remember that the average background that we experience during the year is only 0.4. So we're about 20 times hotter if we're flying than if we just stayed on the ground. Luckily, we don't stay in the air very long, so that's a good thing. But if you're a frequent flyer, or working for Air Canada as a flight attendant or something, 900 hours times 7 micros gives you almost twice the annual radiation dosage you would get on the ground. So that's a problem. It's certainly a problem for stewardesses in their first trimester. And some of the medical studies have suggested that people on the flight deck actually receive, for this kind of exposure long term over the course of 20 years, they have a higher incidence of certain odd kinds of cancers and cataracts and things like that, much like what the astronauts experience coming back in these longitudinal studies. So doubling the radiation above the normal background of the ground is not without its consequence, and I guess that's the takeaway. We have polar cap absorption events which decrease high-frequency communication. That's a safety issue for airline travel, and so during intense storms, basically you wind up having to divert air traffic away from the affected areas, and that's how they deal with that. Forecasting of the sunspot cycle and other things, we'd like to be able to do this because, at least we'd have some sense during what years we have greater likelihood of problems than others. We've had this 11-year cycle for, quite a long time. You would think that we'd know how to model it, and there are many models out there, physics-based models. I'm sure you recognize these equations. I've seen a few of them today. Modeling is sort of the high frontier these days, and the models have gotten extremely good. Thanks to the very high quality data that we get from some of the NASA real estates like SDO and SOHO, and certainly the helioseismology studies that are going on, where we can actually look at the convective zone and the base of the convective zone. Sunspot modeling on supercomputers is now actually turning out things that instead of looking like flowers actually look like sunspots. So you can actually look at the flows and how magnetic flux is being propagated around. And this goes on and on. I'm sure you've seen some of the sunspot predictions based on newer generations of solar models. Apparently, they haven't really played out very well for the 24th cycle. They tend to overpredict just how severe it's going to be, and it looks like it's going to be kind of a runt of a cycle. Certainly not as bad as the 22nd, maybe about half as bad. So there's still problems to be worked out on the modeling side. For transient events, it's much more difficult, mainly because the scale at which the events occur, no matter how good your imaging technology is, the scale always seems to be smaller than your ability to image in time and space. We've been on this constant race to put technology up there, only to discover that we really needed something that had 10 times the resolution in time or space. And so you put another imager up there, and that goal seems to keep going further and further. Now we're at 100-kilometer scale kind of events. At 1 arc-second resolution, we're talking 700 kilometers. So, 1 arc-second or sub-arc-second imaging is definitely what you have to do to make any kind of heads or tails of the plasma flows, magnetic field imaging, and basically the time ordering of events, which is extremely critical in these very fast events and phenomena. CME modeling and cosmic ray modeling is certainly available, and a lot of integrative models are now available that basically pull all these components together. You can even on your iPad, get an app that basically shows you today's model for what things are doing, which is just quite dramatic. Let's see. And as I mentioned before, people that design space systems have radiation modeling. The canonical one is SPENVIS, which is used by just about everybody. And one can adapt this by putting in your own constants and absorption ratios and things like that. So it's a very adaptable and expandable kind of a modeling environment. Forecasting, we have a variety of forecasting systems online at various degrees of resolution. Some are nothing more than just pretty pictures, but very educational for the average public. And of course, there's an app for that. You can get just about any of this stuff now on your iPhone or iPad. So it's now, for the first time, 10 years ago, the general public had no access to any of this, and they had no real concept of things moving around in space and affecting you. Today, if you look at some of the news reports, the reporters at least are a lot more sophisticated. They know how to talk some of the talk of space weather. They routinely talk about coronal mass ejections now without apology. They often get the physics of solar flares roughly correct and things like that. So there's been a real sea change in how space weather events are now reported compared to the way they were 10 years ago, which is good. Societal impacts, putting things on a scale. Some of the big things that the public thinks about are still, the San Francisco earthquake and Katrina. North American power grid blackout would be about $30 billion a day, according to John Kappelman, if the power grid went out because of the space weather event. Geosatellite revenue loss could exceed $25 billion if our geosatellites were affected in some way. And then we have a number of other events, but I have to show you on this scale, the Quebec blackout, about $2 billion in GDP, which isn't really the money that you take out of your wallet. The money that you take out of the wallet replaces the stuff that was in your freezer because your refrigerator stopped working for a day or two. And so if you only take that into consideration, it's far less than $2 billion. But if you look at a typical large annual storm, like a hurricane or tsunami, and we have like 30 or 40 of those worldwide every year, they're about $1 billion a piece. And that's actual property damage, houses leveled, cars thrown into the air, things like that. So, when we try to tell people about space weather impacts, it's like we're still talking a lot of theory to them because they've never seen, geostationary satellites affecting them, to the tune that a small hurricane does on the ground. So they don't have the same sense of urgency about these two things. And that's why, constantly telling people about space weather events is such an uphill climb all the time. Because they just don't have any reference for the scale of catastrophe that could happen if we got the wrong kind of a storm at the wrong time. Worst case preparedness, Kappelman has done calculations since the late 1990s, more recent ones, he's declaring in front of Congress over $1 trillion in GDP loss, and the recovery time now is, several years for a large 1921 scale magnetic storm. And that's not even a superstorm event, which is like the 1859. So this is starting to get into large sums of money. We have Kevin Forbes. He'll tell you a little bit later this next week about the effects that magnetic storms can have on the power grid in terms of actual real money that people in the power industry actually use and how that affects the consumer. We have loss to satellites, Monte Carlo studies, a simulation of the satellite population in the face of various types of storm events. And the gap between those two red lines gives you a general about $50 billion, sort of a range, depending on what model you use and what realization of that model. Preparedness has actually become a very political subject now, and there are a number of references. I would recommend that you pick one of these and adopt it and read through it carefully, because there's a lot of really good stuff in these things. And this is like coming really from the horse's mouth. This is the stuff that congressmen and legislators are looking at more and more, and as well as Homeland Security and the Department of Defense. If a power grid goes out, nuclear power plants are really up the creek, because a lot of the systems that run a nuclear power plant are based on the reliability of the electric power grid outside the power plant. I mean, you've got pumps that move circulating fluid around, and those are not powered by the power plant. They come off of the grid. So if those pumps stop operating, all of a sudden you have heating up of the core and all those sorts of bad things. So the nuclear power industry has gotten into the fray. It's not just a consumer electric power issue, and when you turn on the lights at home, now it's power plant issues. And we have, before there was a threat to the United States from electromagnetic pulse events, but now they broadened that to include geomagnetic storm events. So, and this runs 208 pages. I'd recommend that you read this over a course of time, not in one sitting. They don't have very many pretty pictures either, so you can't kind of just skim. Severe space weather events, there are doomsday scenarios that are now being bandied about, largely having to do with the impact to the power grid. The power grid seems to be the #1 thing that people are focusing on. You can afford to lose a few satellites, and the satellites are so robust, it would be surprising if very many of them failed, even in the face of a large superstorm. Of course, if you lose the right ones, then that could bring everything down. There are only about 5 satellites that carry all of the ATM verification traffic. So if you lose one of those, I mean, you're standing at the gas pump waiting for the card to swipe and the thing to get verified. So the immediate impact is very quick. And also there's a lot of DoD assets that have to be running all the time to keep track of movements of people and terrorists. So it's a real problem for satellites, even a small glitch. And then we talk about things very recently like high impact and low frequency events. And this is basically things like the 1859 superstorm. It's a rare event, one every 150 years or so, but the impact of it would surely be devastating to the power grid in terms of the GICs that would run through the power grid very destructively. I mean, the 1921 magnetic storm produced GIC, modeling would produce GICs that are only about 30% of what the superstorm was. And even with the 1921 model, we lose upwards of 30% to 50% of our power grid for a protracted period of time. So this is big stuff. And it goes on and on like this. There are now quite a lot of studies. Preparedness, worst case preparedness is now kind of in vogue, and the stakes seem higher because everybody's banding around, trillion-dollar impacts and multi-year recoveries with rolling blackouts, and psychologists are now looking at this. We now have psychological assessments on what happens during one of these big impacts, and riots and all kinds of things going on as people adjust to the fact that their lights don't work and they can't get fresh water on a regular basis any longer. But anyway, NASA warns solar flare from huge space storm will cause devastation. Okay, here's a news report. Dire warning, U.S. unprepared for massive solar storm, could lose power, communication. Guy on the cell phone, that says it all with the sun in the background, And then finally we have send us back to the Stone Age, That's LA Times. Yeah, it's got to be the LA Times, right? Well, it would have been more sensible if they were the San Francisco Times, but LA is good. So, that's sort of what we're up against at this point. Space weather is sort of, a new subject. It's not a new subject, it's an old subject, but it's now being repackaged yet again. We did a first round of it back at the beginning of the 23rd cycle, and that seemed to work pretty well. But we never really got anything really great until 2003 when we had the Halloween storms. And then even with the Halloween storms, there were a lot of articles that came out. But you heard a little bit about, 50,000 people in Lund, Sweden, not far from my hometown, who lost power for a few hours. Well, that doesn't sound too bad. I mean, my community could stand to lose some power for a few hours and actually talk to each other for a change. Turn off those flat screen TVs. There were transformers in South Africa that failed within a few months afterwards. And then we had some miscellaneous satellite issues that happened, and that was about it. We had a wonderful aurora. And so that's, for us, the 2003 Halloween storm is sort of like, wow, that was a really big event for us. But for the average person, it was almost a nothing. Certainly if average person living in the United States, I mean, they were not encumbered by a single thing from that event. So, you know, that makes it more complicated. You know, the more you talk about these dreadful effects that could happen with the next bad storm, I think the more the public tends to become, you know, okay, yeah, you know, I remember reading that in the last column you wrote 2 months ago about that storm. You know, so I think we have to be careful how we sell this particular package during this solar cycle. But if it's any you know, sort of consolation, this might be actually the last time we have to do this. Because some predictions suggest that there won't be a 25th solar cycle, that we'll be in a protracted Maunder minimum again. In which case we won't have any solar proton events, we won't have a whole lot going on in geospace, everything will be static just about, you know, and so I don't know. We have one more chance to get this right. Hopefully the sun won't reward us by a superstorm, because that's overkill in more ways than one. But anyway, so as you go about your thinking about the physics and things, you know, think about the impact story from time to time. All right, any questions? All right. That's a really, really cool story. I actually talked to a reporter with the Boston, or the Baltimore Sun-Times. He was interviewing me for something else, and I said, "Hey, by the way, you know, I noticed this interesting effect." And he said, "Oh, you know, that's no big deal. That was the rise of television broadcasting and beginning of the decline of newspaper subscriptions." And what had happened was, apparently, that newspapers reported space weather events because those were things happening right then, you know, and they'd come out the same day and they'd write about it, you know, in the afternoon edition because the thing happened that morning, and so it worked with the news cycle very well for newspapers. But when newspapers started going away, we wind up with a TV industry. The TV industry chose not to report these kinds of events because if something happened like yesterday, it was old news to the TV broadcasters. And until you wait a day, you don't really know all the reports that trickle in for what the impact was. So what happened apparently was roughly around the time that the TV was in its ascendancy, space weather event stories were declining in popularity because they were sort of caught between the cracks. Newspapers didn't want to cover the story any longer because they were fighting for their lives, you know, to keep subscribers. And subscribers only wanted to hear about local news for the most part, not solar storms and not these big things. TV, on the other hand, didn't want to cover it because it didn't fit the TV schedule of reporting news happening right now. And so that's sort of the theory. That's why roughly 45 to 55 we see this change. That, you know, the space weather story goes further into the back of the newspaper, you know, less column inches, more reporting of local murders and, you know, kidnapping and things like that. Today, the situation is a little bit different. You know, we don't have a lot of these old broadcasting technologies anymore. We have the internet. The internet is basically robust against space weather, as far as we know. And that's where increasingly number of people are getting their news. They're not getting it from TVs anymore, for the most part. And you know, you have X number of cable stations, but you have 10 times X number of, you know, internet broadcasting stations. So you know, now it's sort of becoming a story all over again because, you know, when you have internet broadcasting stations, you know, they're trying to fill up time, you know, by the gods. And so these become automatic human interest stories. And so they report them, you know, as you've seen here. Other questions? Yeah.
You mentioned that some of the basic physics that goes into, say, how a solar flare happens or how it, you know, impacts Earth is actually an increase in news reporting. But when we have articles like this, like these sort of like
Well,
Everything is going to kill your children.
yes, but the thing that's so cool about it is that up until fairly recently, the reporters would talk about CMEs and call them solar flares, and they would talk about solar flares and call them solar flares. They didn't distinguish too well between the two phenomena, and the two phenomena lead to two very different types of genealogy for space weather impacts. So at least they're discriminating between X-class flares and CMEs in these reports. They really seem to like the X-class flare reports because, we've got this, they're X, wow, that's cool. And then you get to put this big number after it. Wow, it's cool. So it's something they can hang a hat on. It's an event that happened at a particular moment, and they really like that specificity. So you'll see a lot more reporting about, major X-class flare was sighted on the sun, the biggest one in 10 years, or 5 years, or 15 minutes. I mean, that's internet reporting. 15 minutes is old news, a sort of time cycle. Anyway, yeah.
I have a question. The satellite manufacturers, are they willing and ready to start investing money into prediction and research, or would they rather just?
Well, yeah. Actually, thank you for that comment. Well, nobody really knows because the design of satellites is proprietary, so we really don't know what commercial developers use. And basically, commercial developers include Boeing and Lockheed, which manufacture the large share of the buses that are used by commercial satellite operators, at least operating in geospace. And they have catalogs for what their buses look like and what their capabilities are, but there's no public literature on susceptibilities or modeling or how they develop these things. That's all in-house. The thing that's difficult about space weather, it would be fun if I could get up here and give you a presentation that had a lot of math in it, because I like math. The problem is that with space weather, it's so blastedly frustrating because we're dealing with poorly sampled data that's biased. In the satellite industry, you'll have archives of satellite anomalies. One is actually on your shared drive that I put up. David Wilkinson, back in '94, he accumulated since 1974 an archive of some 6,000 or 7,000 satellite anomalies that were reported to him by friends operating satellites in the military and in the commercial sector. And they would willingly sort of give him this information, and he put it together into an archive, and it's a public archive that you can download and sift through. You'll find a lot of errors that have to do with sudden event, single event upsets and electrostatic discharges, and a lot of unknowns. But that all came to an end soon after 1994. He said by 1998, all of its sources basically dried up. They stopped reporting to him voluntarily and through the goodness of their hearts all this satellite anomaly data. Because what had started happening was that there was the rise of the commercial satellite sector in the late 80s. And so you now have satellite operators and owners not really wanting to report too much about bad things that happen to their satellites that were recoverable things. I mean, most of these problems, these anomalies, were totally trivial things. You reset it by cycling a switch somewhere. Only occasionally, did they lead to real problems. And so, but even that level of candidness began to become very uncomfortable for the industry, and certainly the military, for various obvious reasons. So essentially what we now have is fairly old data archives using old satellite buses that we somehow have to sift through to figure out what current satellite vulnerabilities are on different buses that have been designed since then. We know one thing that has gone on between then and now, and that is today the commercial satellite operators, and to some extent the military satellite operators, are increasingly using off-the-shelf electronics that are not radiation hardened. 15 years ago, the big boast was that we just developed an equivalent to the Pentium processor that was radiation hardened. And by that time, Pentium processors were old hat in commercial computers. But now what they're doing is taking literally off-the-shelf computer technology and putting it into satellites. And here, the calculation is, the satellite fails, the satellite is so cheap because it uses COTS that we can just launch another one very quickly. And meanwhile, we have enough transponder redundancy on affiliated satellites in our country that we can just move our customers from the damaged satellite off to the other one, within an hour, so the customer isn't affected. So they look at it that way, that there's no longer any real reason to make their satellites more radiation hardened, and there's every incentive in the world to launch cheaper technology that they can replace more often. Even though it sounds like a completely stupid thing to do, it makes sense in the commercial world. The equivalent exchange in the military sphere, I don't know what that is. But it's the idea of data secrecy, and that's what we're really hamstrung with. We realized there was a problem at the beginning of the 23rd cycle with getting access to what satellite buses were vulnerable to things, because they served as interesting test particles in the magnetosphere that we could use to understand our magnetospheric models a little bit better. But now in the 24th cycle, we have comparatively less of this data available to us on newer generations of even more vulnerable buses. And that's not a desirable place to be, but economically it serves some kind of a purpose. Long answer, short question, sorry. Yeah. That's an interesting story. I'm sorry. If a satellite actually fails, what does the company and the owner do about that very public situation? How do they react to that? Well, we have a number of incidents where a satellite would fail, even in the 23rd cycle. And the initial report from the company was it was a space weather event caused by something that happened on the same day or within hours, on the sun. And that was good. Okay, cool. That happens in space. All right, that's logical. But then all of a sudden, weeks or months later, the official story becomes, it was a manufacturing defect in the satellite, which we're not going to make in the next generation. So basically, they moved it away from being a space weather caused event to being just an internal manufacturing error that, we'll take care of it. Also, using a software problem is a common thing. We had the Galaxy 15 a couple of years ago fail in a full power mode, which is kind of bad. You have this full power, geosynchronous satellite, without position lock, beaming its power into other satellites near it. So they called it the zombie satellite, Zombie Sat 1, actually. The initial report, within a week after this event happened, or within days after the event, the company Intelsat said this was a space weather event caused by a solar flare that happened the same day. All right, fine. And then all of a sudden, a couple of months later, they say, it was a software error that we fixed, and we're going to be able to fully recover the satellite by early 2013 and put it back into full use. Well, okay. A single event upset is a space weather event. You can resolve it by doing a software reboot, but that doesn't make the event a software issue. It's still fundamentally a space weather issue that you have repaired by a software, fix, by resetting something. But that's sort of the subterfuge that they're using. Now the story for Zombie Sat 1 is that it basically was a software glitch that they have fixed. It's no longer a space weather event, which happened proximate to an actual space weather event that day. So, it's this process that the commercial sector does and has to do in order to establish that they have a fully reliable resource that any customer can rely on round the clock, 24/7, 365, and not impugn its operability by it being affected by some external factors. So it's a kind of a bizarre story. And that's probably why the whole subject of space weather forecasting, perhaps, in terms of the impact side, has sluggishly developed, over the last 20 years, because it is so mired in what amounts to anecdotal evidence, you know, and voluntarily reported errors on satellites by institutions that don't want to report fallibility on their hardware. You know? So that's what you're up against, you know, when you talk about space weather and impacts, that most of the really good impacts you don't know about, but they're probably inconsequential anyway. And the real impacts that happen are probably going to be explained as being something else anyway. But the power grid, now that's something that you can't walk away from. The cool thing about the power grid is that it consists of, you know, 10,000 elements that are far more homogeneous than the 2,000 satellites operating in orbit. Every one of those satellites is a different beast. It's almost hand manufactured for specific things with specific technology. So you've got, you know, 2,000 of these particles up there, each with a different way of transducing a space environment event. With transformers on the ground and capacitors on the ground and power stations, they are a much more homogeneous sample of things, because generally they're manufactured by 2 companies on the planet. I think one in Tokyo and the other one's in Austria. They're the only 2 companies that make these big transformers any longer. And they basically stamp them out. You know, so power grid modeling is probably going to be a much more robust thing for us to be doing, and the consequences are probably quite a bit higher than satellite modeling anyway, for which most of the data is hidden from us. Anyway, final comments. So, okay, that's about it. Thank you.